All right, hello physicists. Welcome to our April 12th edition of physics. Friday's quiz was good. There's only one question that people had some problems with. The torque is defined by R cross F, and it's a vector. In this one, to determine the direction of the torque, you have to use your right hand. And so on our bottom bracket, this would be pointing out of the page, R cross F. So there's your R, there's your F. And do your right hand rule, and you find that R cross F and coming out. So my torque here is out of the page. And then here the torque is R cross F into the page. Okay, and this is equal to the size of R times the size of F times the sine of the angle between them. So in this case, the angle is 90 degrees. So the torque into the page, it would be it would be 2L times F times sine of 90 degrees, which is just 2LF. On the other hand, my torque out of the page would be L times 2F times sine of 45. So that one would be 2LF, but then times square root of 2 over 2. And so if you take the difference of those two, that's where you get this. Okay, so that should be 2 times 1 minus square root of 2 over 2, or 2 minus square root of 2. So this is 1 or 2 minus around 1.4 times, this should be times LF times LF, and there you go. And into is bigger than out of, so the net torque is into the page. Now the purpose of this video is to try to get us ready for the test. Today you have your last homework that you're supposed to be submitting. If you have questions, please email me. I'm not super, if you get it in a little late, that's fine. But we are taking a test this Friday, so it's a good idea to try to get that done and then start working on review. So today's video is all review stuff. And I have put up a Unit 3 formulas sheet on Canvas, and it's a good exercise to try to understand every single formula that's on there, and that's a good way to review for the test. So that's sort of what this video is about. So the test is over Chapter 9, Chapter 10, Chapter 11, skip Chapter 12, and then parts of Chapter 13. Okay, so it's quite a bit of material, and we want to make sure that we have some understanding of it. Okay, so Chapter 9 talked a lot about the center of mass. I don't think I'm going to put any of that stuff on the test. It is important for understanding how we can treat extended objects as being a single point object, though. What we spent more time on in that section, though, was the idea of momentum. Momentum can have a direction. So P has the same direction as V for an object, and it's weighted by the mass. And the reason why it was helpful is that we could rewrite Newton's second law instead of just having F equals ma, although this is the same thing. This is F equals ma rewritten. We could write it as the change in the momentum per unit time. And if we integrate it over the time, then what we found was that the change in momentum for a particle was equal to the impulse. And the impulse is just the average force multiplied by the amount of time. Okay, so this is mv final minus mv initial. That's what your delta, your change in momentum is. And this is a vector quantity. So just to say that in more words, if you apply an impulse, you get a change in momentum. And the classic type of problem to do with this, that I've put problems in here that I just recommend you review, because I know you've done them already. But in this one, for instance, it says that we've got a force in the negative x direction. Okay, so that's an important piece of information there. It says the force varies in magnitude and the impulse has a magnitude of 32.4 newtons times second. So in this case, J, the impulse, is in the same direction as the force. So if the force is in the minus x direction, the impulse would also be a minus negative quantity. Okay? So that's if I write it as a vector. And in this case, if you want to use your impulse momentum theorem, your impulse is equal to the change in momentum. So that's going to be mv final minus mv initial equals j, and you have to keep the sign, so it matters that this is a minus sign, and it matters that v initial they give us as do they give it? Yeah, plus 14 meters per second. So when you're doing these, you always have to be careful about the direction of the speeds, so that you're treating them as real velocities. And v final is what you don't know. The mass of the ball is 0.40 kilograms. Okay, so you could plug this in, use your mass, and find this. Okay, and I believe when you do the problem, you find out that this has a negative, VF is negative. So that means that after getting this impulse, our ball moves in the direction that it was pushed. Okay, so yeah. So just be aware that the direction matters. The direction also matters in problems where we are concerned about conservation of momentum. So this is the type of, so the impulse momentum theorem is what we use when we have an external force acting on a ball. Conservation of momentum is the type of thing that we use when we have a bunch of particles that are interacting amongst each other, but there's no external force coming into the system and acting on them. And so if you add up the momenta as vectors, add up mv, 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 where v is a vector for each one of them, you get overall system momentum is conserved. So before a collision and after a collision, for instance, you can set up these equations. Now we class our types of collisions in two sorts. One was the idea of an elastic collision. One was the idea of an inelastic collision. And an elastic collision was one where if you took the kinetic energy, so like 1/2 m1 v1 squared, v1 initial squared, plus 1/2 m2 v2 initial squared, it would be equal to 1/2 m1 v1 final plus 1/2 m2 v2 final squared. Okay, so this would be the definition of an elastic. If you have kinetic of the initial is greater than the kinetic of the final, that's the typical case for inelastic. Okay, And of course, you can have other situations too. If you have, for instance, a bomb that blows up, if there's extra chemical energy that's put into it, then you can have situations where you have zero momentum, and then both of the sides of the ball blow apart, and then the momentum is still conserved. So you can have all sorts of cases like this too. Now, the type of problem I like is, I do like this ballistic pendulum sort of problem. I can imagine putting it as a short answer question on a test, where you have, in the initial phase of this, you have momentum being conserved, and then in the final phase of it, you have energy being conserved. So we'll look at that problem just briefly. So here's the type of problem that you would set up for a momentum conservation short answer type of question. It gives you the initial velocity of block A and block B, then they collide, then you're given the final velocity of block B after they've stopped touching, and you're asked to give what the final velocity of block A is. So in this case, if that velocity you find is positive, it's moving in the positive direction. If it's negative, it's moving in the negative direction. And then it asks, is the collision elastic? So, all right, in this one, by the way, you just use this sort of an equation because you're given your VA initial, and your VB initial, and your VA final. That's the question mark, and then VB final is 4.9 meters per second. Okay, so when you set this up, and you've got, of course, a mass of A, a mass of B, where they give you those. Okay, so you set up a equation where you add up the mass of the velocity of A times the mass of A, velocity of B times the mass of B, equals, and then the same thing afterwards. And then you can use that to solve for V. And then what you can do is, this would be very much a question mark. You don't know if the collision is elastic or not. So what you have to do is you have to add up the kinetic energy of both particles beforehand, add up the kinetic energy of both particles after their collision, and if it turns out that the numbers are the same, then the collision is elastic. If it turns out that they are not, then it is inelastic. So as I said, I like the ballistic pendulum problem. The way that this works is that you start out with a little mass, and that's your bullet, and then big mass, which is your block. And the problem has two parts because your bullet starts out with some speed, and then it sticks into the block, and so the final mass that you deal with is the m plus m, so that's the mass of the bullet stuck into the block, and it's going at some speed v. So once that happens, this is not an elastic collision. It sticks into the block, and that causes heat losses as the bullet tears into the wood. On the other hand, you can use, after this collision, you can use some nice regular old energy conservation to do your 1/2 m plus m v squared. So you start out with the kinetic energy of the ball or of the bullet and the block stuck together, and you end up with m plus m g h. So you end up with the block having gone upward, and it ends up with some potential energy. Okay, so it's a nice simple problem, but I can imagine putting it on a test. All right, so that's our first chapter. What do we do next? Well, what was tricky next is that we started to think about motions of extended objects. So here's like a disc, a wheel or a record or something like that. And we suppose that this disc is spinning in some way. And what's interesting about this situation is that if you look at a particle on the inside versus the outside of the wheel, they're moving around at different speeds. This object is moving less distance, so it's moving slower. This object is moving more distance, so it's faster. But since the whole object is all glommed together and it's all moving as one unit, it would be convenient to introduce the type of notation where the two parts of the object would be recorded as being at the same speed. Okay, so you introduce this kind of made-up notation where where we only keep track now of how many degrees per second, or how many radians rather, we're moving. Okay, so we can relate this just to the actual position, how far it's moved, by dividing it by the radius. And this is r is relative to the axis of rotation about which the object is spinning. Same thing with v, same thing with a, and we went from, so essentially we're going from x to theta. So this would be in meters, this would be in radians. We're going from v to omega. This was in meters per second, that's your velocity. This is in radians per second. And as a convention, we have that our v was a vector, and we also have, surprisingly maybe, omega as a vector. And the way that you make it a vector is with your right-hand rule. You have your hand spin around in the direction, and your angular velocity points in the direction of your thumb. And then for our our acceleration, meters per second squared, we go ahead and we have alpha radians per second squared. Now, just to be clear about this, this a is a linear acceleration. It's telling you how your linear velocity is changing. This alpha is only telling you about how this angular velocity is changing. So it doesn't include that centripetal acceleration, v squared over r. That was directed towards the center of the circle. This is about the velocity, the accelerations that are tangential to the circle. So if your spinning is speeding up or slowing down. Okay, so there's this other part that this is all about your tangential acceleration, and this is all about your centripetal, or towards the center of the circle, acceleration. Okay, so using this map, x to theta, v to omega, a to alpha, we were able to do problems using angular constant acceleration as a model. And we just stole all of the work that we did earlier for our constant acceleration in a line, and transposed it, transposed the x to theta, v to omega, t stays the same, a to alpha, and there you go. Now, as I said, this is just acceleration. The acceleration that we're talking about is how your speed around the circle changes. It doesn't have to do with this radial acceleration, which we already understood to some extent. That just depends on your instantaneous speed. All right, so this type of a problem would be probably a good one for a multi-part short answer type of question. Take a look. It says the original Ferris wheel had a radius of 38 meters. So I think I've done this problem before, but it's It's a little bit tricky to think your way through. And completed a full revolution 2 pi radians every 2 minutes. So omega equals 2 pi over 2 minutes. And it's good to get this in terms of radians per second. 1 minute is 60 seconds. It says if the wheel were uniformly slowed from its maximum speed to a stop in 35 seconds, okay, so if you had your omega, this as your omega naught, and your omega final is 0 radians per second at a time of 35 seconds. It says find out what would the magnitude of the instantaneous tangential speed of the outer rim of the wheel be 15 seconds after it begins its deceleration. So you want to find this omega at 15, and then once you find that, you can take your linear velocity at that 15 seconds is going to be r times the angular velocity. So essentially what you need to do to solve this sort of a problem is you need to set up your omega equals alpha t plus omega naught. Okay, then you could use this and solve for alpha. That's your angular acceleration. It'll probably give you a negative number. And then you go ahead and stick in this and stick in that and put in at 15 seconds and use your original omega naught again, and that would give you the omega at 15 seconds, and then your v at 15 seconds would be just r times omega at 15 seconds. Okay, and our r would be 38 meters. Okay, so that's a good problem to review just because there's a lot going on. Now, something that we did next in our unit is that we talked about what is the kinetic energy that is stored in one of these rotating objects. Obviously, the stuff on the outside is moving faster, so it has a bigger kinetic energy. The stuff on the inside is moving slower. But what we did was we rewrote the, instead of just thinking about the total mass and having to think about each little piece of mass individually, what we could do is think about m times r squared, and then we could come up with an expression for the kinetic energy that looks essentially like what we're used to. Remember, we're used to using k equals 1/2 mv squared. Well, here we have k equals 1/2 I omega squared. So even though different parts of our disk are moving at different speeds, we can talk about our disk in terms, or we can talk about the kinetic energy of our spinning object in terms of the angular velocity. So that's a nice conceptual simplification. Now, I'm not going to ask you to calculate a lot of difficult rotational inertia. I do want you to be able to understand, though, what's the difference between spinning this way and spinning this way. And it has to do with this mr squared. If your mass in your object is farther away from the axis of rotation, you're going to get a bigger moment of inertia or rotational inertia. So in this case, I would expect to have a smaller rotational inertia than if I spin it out like my pen out like this, because more of my mass is at the edges in this case when I'm spinning it lengthwise rather than along its long axis. Okay, so this is a problem that might get you to start thinking about some of this stuff. It says what's the magnitude of the rod's angular momentum, or sorry, angular acceleration. Well, it gives you omega versus t, and if you wanted to find your alpha, it's just your change in omega over change in t, or in differential terms, d omega dt. Okay, so you take the slope, and then it asks at 4 seconds the rod has a rotational kinetic energy of 1.60 joules. So you can go ahead there at 4 seconds, look at what the omega is, and use the kinetic energy is 1/2 I omega squared. It's a 2. And you could go ahead and solve for I, even if you didn't necessarily know the details of the geometry in this case. Okay, now we started, I believe the way that we introduced the idea of moment of inertia is with this kinetic energy, but it turns out to have lots of nice extra properties. And one of the nicest of them is that I can rewrite Newton's second law in terms of it. And so we are used to having Newton's second law as F equals ma. But here, if I instead of using forces use torques, this is going to be, the torque is going to be defined as R cross F. And you'll remember we did a problem with this at the beginning of this video. But the torque is not the mass, but the moment of inertia times the angular acceleration. And so by starting that in that place, you can go ahead and sort of restate the theorems that that we figured out in terms of linear motion in terms of angular motion. So, for instance, instead of having just work energy theorem, we have the angular work energy theorem, where the change in our kinetic energy final minus the kinetic energy initial is how much work we put into our object. The amount of power that in the linear regime, we had this as, so this was the same, the amount of work that you're putting in per unit time, but instead of having torque times angular velocity, it was just force times velocity. So some similarities here. Now, as I said, I'm not going to force you to memorize all of these. I give them to you on your equation sheet, so please take a look at your equation sheet, make sure that it makes sense. I do think a question like this is quite fair. This is three different objects. One of them is a ball on a stick that's rotating 1 meter away. One is a ball on a stick that's 2 meters away. One is a ball on a stick that's 3 meters away. And you might remember this example from our PowerPoint a couple weeks ago. And in this case, I equals 36 kilograms meters squared for each one of these cases. And the takeaway from this is that if you have a much bigger mass that's closer to the axis of rotation, it effectively acts sort of like a much smaller mass that's farther away from the axis of rotation. And as I said a little bit earlier, for the Newton's second law, you really do need to be aware that this acceleration is different from the centripetal acceleration that we've been looking at otherwise. So it's just this torque equals I times alpha. It's just giving us the acceleration going around the circle where one of our points is fixed. So, for instance, I think a problem like this would be pretty fair. I could say find the net. For instance, this one just asks you for net torque, but I think it'd be fair to say for these two types of forces, find the net, find the angular acceleration or something like that. So in this case, your R cross F, this would give you a torque out of page R cross F. This one would give you a torque in the page. So T1 is going out of the page, T2 is going into the page. And remember, this point we are assuming is fixed. We put a thumbtack through it or something like that. And so you would have to, this F1 is trying to get this object to spin counterclockwise. F2 is trying to get the object to spin clockwise. So you'd have to take the difference of their two torques to get your net torque. And then that would be I times alpha. So in this problem, they just want you to find this by using your force times distance to the axis of rotation times sine of the, I'm going to use the same notation here. So you have to be careful that it's the sine of the angle between the two. So there, this is your R and F, and it's this angle like this. R F1, R F2. There's your angle 2. It's the same as theta, but just to be aware that you could be given the angle in a tricky way. Okay. All right, so as I said, we have done the rotational work energy theorem. We've done the power, and let's see. So if I gave you a problem like this, it would be fair game. It says a 32 kilogram wheel, which is essentially a thin hoop. So if you see words like that, that should trigger an alarm bell and say, ah, I need to go look up what the I is. So it's just mr squared in this case. And they give you some information. They give you the R. They give you the omega, but that's not great the way they've given it to us. 280 revs per minute. I would like instead to have it in radians per second. So 1 minute would be 60 seconds. Okay, and then for instance, they ask how much work must be done to stop it. Well, I could go ahead and, you know, I would get, if you have it stopped, then that final would be 0, and then you do 1/2 I, which would be this. They give you the mass as well. Okay, 1/2 I times omega, so that has to be in radians per second squared, and that would give you your work. And if you divide it by the amount of time that it took, that could give you the power. Okay, so after that, we looked at the process of rolling. And a rolling motion is sort of a sum of a pure rotation plus a pure translation. The tricky thing about rolling is that if this point is sticking, that essentially is your axis of rotation, whereas everything that we worked on was sort of thinking about this wheel going around the center here. But we used some clever tricks, and we found out that you can write out the kinetic energy of this in terms of the moment of inertia about that center of mass, if you know the omega, and then the 1/2 mv squared. That looks like just the kinetic energy due to translation. And of course, it's a little interesting because the top of the wheel is in fact moving more quickly than the bottom of the wheel, because this essentially is your instantaneous axis of rotation in that case. So I encourage you to remind yourself how to do this problem. Try to get out 27 joules. We did this in class just a little while ago. So make sure that you can do this type of thing. The sort of the last thing that we did with angular movement was this idea of angular momentum conservation, where here you have a big moment of inertia because I is the sum of all your mr squared for all your little points I. And so these masses being out gives you a bigger moment of inertia than over here. So here, if you have a big I, that means, and if your product of I times omega is constant, here you have a little omega, here you have a big omega. And the product of this I times omega is the same before and after. So for instance, in this problem, it says the rotational inertia of a collapsing spinning star drops to 1/3 of its initial value. Okay, so I goes to 1/3 I naught, and you want to find how did your omega change? Well, if your I naught times omega naught equals I omega, and you have your I change to 1/3 I of your initial I, then your omega has to go to 3 omega naught. Okay, so there you go. And in class we solved this second part, but this is the most important part of the problem to understand. Okay, now our very last topic, I know I'm kind of rushing through things, but we've done a lot, and I don't want to make this video too long. The last thing we did was universal gravitation. As I said, this is my one of my two favorite equations in this class. If you remember F equals ma and Newton's law of gravity, that would be a good outcome for this semester. For me, for you. Okay, and so what it is, it says that if you have two objects, mass 1, mass 2, and they're separated by some distance r, well, mass 1 is pulled on by mass 2 is pulled on by mass 1, and they are equal sizes of forces, opposite directions, and the force is going to be g m1 m2 over r squared, and g has to have funny units, 6.67 times 10 to the minus 11. Okay, very small number because gravity is relatively quite weak compared to, for instance, electromagnetism. And if we want this to have units of force, force has units of newtons, but then we have to cancel out the r squared, so we take it times meter squared, and we have to cancel out the kilograms times kilograms on the top, so we put a kilogram squared on the bottom. Now this is a very interesting subject because it ties together many different things. For instance, it ties together projectile motion and orbital motion. In this picture, if you just shoot this gun off hard enough, the ball continues to fall as it traces the surface of the Earth. And this allowed us to find Kepler's law of periods, that the amount of time it takes an object in orbit to go around is related to the mass of the object that's being orbited, not the mass of the satellite, but the mass of, for instance, the Earth, and the distance from the object being orbited, from the center of mass of the object being orbited. So for instance, here is a homework problem I gave you. I like this type of problem because you've got a force in this direction, you've got a force in that direction. So we're thinking about the gravitational forces on B. B is being attracted to A, and B is being attracted to C. And if you wanted to take the F net here, it would be FA in the x direction and FC in the x direction, rather. FA in the y direction, and the size of that F net would be, I would have to use the Pythagorean theorem. Okay, so I know that these types of problems are sometimes hard because you're using such big numbers, but I think a problem like this where we're not using extreme numbers, the only funny number is going to be g, which has a 10 to the minus 11th, causing all of our gravitational forces to be quite small. I think that would be pretty fair. I also like the type of problem where you have to think about where g comes from. Okay, so it just comes from the mass of the Earth and how far we are from the center of the Earth. And for instance, a problem that you solved on your homework today was where that g would be half of what it is, half of that 9.8 that you get on Earth. And you can, of course, just solve for that r. And so I would like, and I'm not making a promise, but I am thinking about putting a homework or a short answer question on the test about g, about t, about force. Okay, so that's a lot of stuff already. What are our big ideas? If you have a closed system, both linear momentum and angular momentum are conserved. For extended bodies, it's useful to introduce collective rotational coordinates, and Newton's law of gravitation ties together many phenomena from projectile motion to satellites. So please get me your homework, your latest homework as soon as you can, and yeah, I will try to put up a review packet for this exam that's this Friday. I'll try to get it done today. If it's not done today, I'll for sure get it up tomorrow. Okay, so thanks for watching, and good luck.